Okay, here we go. So we are going to talk about, hi, first of all, put my tree behind me because it's nice. And hopefully it'll be kind of quiet in here. We'll see how it goes. I'm in the middle of my living room and I don't have headphones in. And right now there's not many people around, but that could change anything. So this week we're going to talk about 2.4 again. Um, but we're specifically going to talk about the second half. So the empirical rule and Chebyshev's theorem, which is a funny word to say. Chebyshev. That's somebody's name, and they came up with this theorem. So a couple weeks ago, we talked about section 2.4a, where we were looking at range and using technology to find variance and standard deviation of a population or a sample. This week, we're going to interpret and try and understand what the heck do those numbers mean and how to use them. If you want to go back and look at that presentation, you can click on here. And here's a quick reminder in the TI-84, remember how we find the mean? This was the mean. And this one would be your sample standard deviation. If you needed the population one, you would look at this. And remember in the last video and in the last presentation, I walked you through how to do that. I just kind of wanted to remind you, jog your memory for a second. So first, let's talk about what the heck an outlier is. We've said before that's a strange number or an unusual number in your data, like when we did the average age of the students in the room, and then we threw in Miss Flannery's age, right? Everybody else was either was somewhere between 16 and 20 years old, and then Miss Flannery pops in and is 42, right? And that 42 is an unusual answer compared to all the other answers that were around 16 to 19 years old. But just saying unusual is kind of hard to measure. So they came up with a few different ways to specifically talk about outliers. And one of the ways that we're going to talk about right now is if the number is more than 2.5 standard deviations, either bigger or 2.5 standard deviations smaller than the average. So it's about how far away is it from the average, not just is it a weird answer, right? So now we can kind of calculate it. So let's look at an example. We're considering the numbers 26 and 11. And we want to see, are those outliers if a sample of data had a standard deviation of 3 and a sample mean or average of 18? Are either of these pieces of data, the 26 or 11, considered to be possible outliers? So there's different ways you can look at this, right? Let me grab my pen and draw something. But first, let's just talk about what we're saying when we say that it has a sample mean of 18. So there's the average. And one standard deviation away, what's 18 plus 3? Well, that's 18, 19, 20, 21, right? So that'd be 21 is the next bump up. If we do another bump up, we add 3 again, we get 24. We do another bump up. When I say bump up, I'm specifically adding a standard deviation. So I'm saying you add another of this number that they told me is 3, right? We're adding another bump, a standard deviation of 3. So if I add another one, I would get 27. Now in the other direction, and we're starting with 18, right? Because that's the average. Now if we go in the other direction, we would subtract 3, right? Because 18 is going to be probably ish in the middle, kind of in the middle. So if we go down, let's see, 18 minus 3 would be 15. Minus 3 would be 12. Minus 3 would be 9, right? So if I said, what are some numbers what's a number that is 3 standard deviations from 18? Well, 3 standard deviations. Let's go. 1, 2, 3 to the right is 27. 1, 2, 3 to the left is 9. So if we're talking about anything outside of 2.5 standard deviations, we could just multiply 2.5 times 3. Okay, so 2.5 times 3. Let's see. 2 times 3 is 6 plus another half. So it'd be 7.5. And then add it and subtract it from that 18 we're talking about. So 18 plus 7.5 would be what? 25.5. 18 minus 7.5 would be 10.5. So we're saying that to be considered an outlier, it has to be bigger than 25.5 or smaller than 10.5. That would be more than 2.5 standard deviations away, because this 3 is my standard deviation, right? And we're talking about how far away are they from 18. So figure out what 2.5 times your standard deviation is, and then add it and subtract it from your average, and then see, are the numbers we're talking about bigger or smaller than that? So let's look at this. So 26. Is 26 smaller than 10.5? No. Is it bigger than 25.5? Yes. So if it's outside, if it's more than 2.5 away, if it's bigger than 25.5, then yeah, it sounds like 26 could be an outlier. That would be a suspect outlier. Let's look at 11. Is 11 bigger than 25.5? No. Is it smaller than 10.5? No. So it doesn't sound like it's an outlier. Sounds like it's right within most of the data. Another way to think through this would be, and I'm going to use my pointer. No, I'll just do this. Would be to think of it like this. So think about how far away is 26 away from the average, the 18. Well, 26 minus 8. And then how many groups away is that from the middle? We'll divide that by whatever the standard deviation is, and that tells you it's 2.7. And they're telling us it has to be more than 2.5 standard deviations away. 2.7 is bigger than 2.5. So yes, 26 is a possible outlier, right? I showed you one way to do it, and now I'm showing you another. And if we look at 11, same question that we could do. How far away is it from the average? It's 7, because do the average minus that number, right? 18 minus 11. And then how many standard deviations away is that? Well, it's only 2.3. And 2.3 is smaller than this 2.5 that they talk about up here. And if it's smaller than that, then no, it's not a likely outlier. We don't suspect that's a weird answer. It falls within most of the data. So now let's talk about how to interpret the standard deviation thing. So the more spread out the entries are, the data is, the bigger the standard deviation. And so it's a way to measure how spread out the data is. So let's look at this one. First of all, before we see anything else, what the heck are they telling us here? Well, they're telling us that the average is 5, and then they're telling us that it's not spread out at all. But when you look at the graph, that seems obvious. All the answers are 5. There's 8 answers, and they're all 5. So 1, 2, 3, 4, 5, 6, 7, 8, right? If we wrote down all the answers, the data, it would all just be a bunch of 5s. It'd be 8 of them. So that's not spread out at all, right? Let's look at this one. This time they're telling us that the average is 5, but now it is spread out a little bit. It's telling us it's spread out a little bit more than 1. So, okay, if I look at the graph, I believe you. What are all the actual data entries? What would the original data have been here? Well, it looks like there's one number 3 here, right? There's one of those. On 4s, there were 2 of those. So 4, 4. 5s, it looks like there were 4 of those. So 1, 2, 3, 4. And then there are 2 6s. And then there was 1 7. Whoops, that's supposed to be a 7. It does not look like a 7. Let me try again. Let's try that again. See, erase. And 7. Okay, so all this stuff that I just drew on here, all of this up here, that's the original data that is grouped in this frequency chart where it says there's one of these threes, there's two of these fours, there's four of these fives, right? That's why I wrote those out. And so, yeah, this is a little bit more spread out. They're not all the exact same answer like they were here. So, okay, I believe you. 1. Okay, great. Fine. Now let's look at one more example where this time we have the mean is still 5, but this time it's spread out a little bit more. See where it says it's about 3? And when you look at it, yeah, that is spread out way more than this, right? And let's write out what if they had asked us what would the original data be here. Well, we've got 3 of these 2s, so 1, 2, 3 of those. We've got 1 of these 3s, 1 7, and then 3 8s. Oh, I ran out of room. So this is the original data down here. Okay, so just trying to help you remember what these graphs mean compared to the original data, and now what this mean and standard deviation tells us. And they could use this little s, and that means sample standard, or they could use the little sigma, which means the population standard. Okay, so without calculating, estimate the population standard deviation of each set. Population standard deviation. So we're going to be using the symbol that looks like this, not the letter S. Oh, that's terrible. You try again. It kind of looks like that. That's a little bit better. It looks like a cursive O. So let's translate this. All right. So all the data here, it's just a bunch of 4s. That's it. That's the only data. So that population standard deviation should be nothing. Okay. This one here, it looks like it's a little bit more spread out. So if the average is still, whoops, my bad, let me go back. If the average is still 4, I pushed all the wrong buttons. My dog. If the average is still 4, let's see, most of the data here is you just added 1, right, to get 5. And here we subtracted 1 to get 3. So most of your data is either adding 1 or subtracting 1. So as far as how spread out it is, it's kind of pretty close to 1 is what my guess would be. My guess would be is that standard deviation is about 1. It either goes up or down 1 number from 4 to 5 or 4 to 3. On this one, the average is still 4, right? Here's the average. But there's some stuff that's a little bit more spread out. So it looks like, let's see, to get to 5, we added 1. And then to get to 7, 4 plus 7 minus 4 is 3. So we added 3 here. We subtracted 1 to get to 3. We subtracted 3. We're talking about compared to 4. Well, you add 1. So all this stuff is either adding or subtracting 1 or adding or subtracting 3. So when it was adding or subtracting 1, when all of it was adding or subtracting 1, standard deviation was 1. If I'm adding or subtracting 1 and 3, then maybe what's between those? Maybe 2. So my guess is that the standard deviation here would be about 2. Okay? That kind of makes sense. So now we're going to look through the official answers for all this and how you get them. And just going to kind of skim through what I just said. On that first one, the height of all of the answers, each of the 8 entries was 4. All the answers were 4. So there was no spread at all. So yeah, the standard deviation was 0. And that's what we said when we guessed. Remember? That's what I said when I guessed. That's right. Look at the next one. Each of the 8 entries has a deviation of +1. Or -1. They either went up 1 or they went down 1. So the population standard deviation should be 1. And if you calculate it using the crazy long formula or a calculator, then the answer is exactly 1 for this one. On the third one, each of the 8 entries has a standard deviation of either plus or minus 1, right? These either went up 1 here or down 1 here, right? Or they went up by 3. So they either went up by 3 here or they went down by 3 here. Whoops, I was about to write 4, but I meant 3. That 3 looks terrible. So my guess was 2, right? And if you use a formula, it's a little bit bigger than 2. In this case, it's 2.2. If you use a formula or the calculator, it would tell you the exact answer, but our estimating was pretty good. It was about 2. We're good to go. Now we're going to talk about 2 rules or theorems. One is called the empirical rule, and one is called Chebyshev, which is kind of fun to say. And it's all about understanding standard deviation and kind of making sense of what it tells us. And so the empirical rule, I'm going to read to you what this says, but I'm going to show you a picture to make it all make sense. That basically, if you have a symmetrical bell-shaped distribution, okay, about 68% of the data is pretty close to the middle. About 95 goes all the way out a little bit more. And then about 99.7 covers almost the whole thing. And here's what I mean by that. When we go out 1 standard deviation, if you either add 1 or subtract 1, right here, from the mean, right? Here's our average. If we go up a standard deviation or down, we're going to cover about 68% of our data. If you go up or down, whoops, my bad, wrong buttons there. If you go up or down another standard deviation, you go out 1 more group, then you're going to hit 95% of the data. And if you go out a 3rd group, you're going to hit 99.7% of the data if you have symmetric distribution. Okay. So let's look at an example. We're going to talk about this. So a survey was conducted by the National Center for Health Statistics. They're talking about average height of women, and it was 64.2. Okay, so if I was going to draw this real quick, let me just go ahead and do that. I'm going to draw this. I'm going to have some sort of bell shape here, and 64.2 is going to be right in the middle. Okay. And it says a sample standard deviation was 2.9. So if I draw the rest of this out, if I go up 1 group, that's going to be whatever 64.2 plus 2.9 is. I got to think really hard. Hang on. 64.2 plus 2.9. That's 11, 4, 5, 6, 7. Hopefully I got it right. 67.1. If I go up 1 more group, I'm just going to add 2.9 again. 2.9. That'll be 70. So this one would be up here at 70. Okay. This is me trying to sketch this beautiful little curve with the right numbers in the right spot. Okay. So this is at 70. This is at 67.1. Now let me go back the other direction. I do 64.2, but I subtract 2.9, the standard deviation, right? Subtract it. If I did 64.2 and I subtracted 3, that would be 61.2. So 61.3, I think. Hopefully I did that right. We'll find out. 61.3. And if I go back one more standard deviation, which is 2.9, right? 61 minus 3, 61, 60, 59, 58. So 58.3. Don't subtract all of that. So 58.4. So that would be this guy right here. I'm sorry, my handwriting is terrible on here. It is what it is, right? So now I've got this group, and let me figure out what are they actually asking me. They said, estimate the percent of the women whose heights are between 58.4 and 64.2 inches. Okay, well, here's 64.2. Here's 58.4. So we're talking about from here to here. They want to know what percent of the women are in this group from here to here. Okay. Well, according to this empirical rule up here, since they're telling me that it is normal distribution, then this carries 34% of my data, and this carries 13.5%. So I just have to add both of those together. 34 plus 13.5. My dog. 34 plus 13.5, which is about 47.5. 47.5%. Whoop, go back. So to answer their question, estimate the percent of the women whose heights are between 58 and 64. Well, it's about 47.5%. Okay, because 58 was 2 standard deviations away. So it went all the way over. There's one standard deviation, there's one jump, and there's another one. So that group carries 3.5%, and this group carries 34%. So add them together. Excuse me. Now we're going to look through how they worded it in lots of words and lots of pictures. So they drew the graph that I did, except more precisely. And then they got more specific and probably used a calculator to come up with these percents. We are going with about 34 and about 13.5. And so they're saying that here's where they get down to. So they said, we said 47.5, they said 47.7 because they did a little bit more precisely. But they did the same idea. They added those 2% together that they got, 13.5 and 34. They used a calculator to come up with some more precise percents. We're just going to use them 13.5 and 34. Okay? Okay. Now, Chebyshev's theorem. Now, if you remember, empirical rule can only be used for symmetric distribution. It has to look like that bell curve. But Chebyshev, which first of all is a cool name, can be used for any distribution. Now, I'm going to show you this part, and it's going to be confusing, but then we're going to get to the bottom line. Okay, don't forget. So it says that there's this formula. It turns out that for any distribution, any shape, right? It doesn't have to be a bell curve anymore, although it's true for a bell curve. It can also be true for something that's skewed or something with bimodal, anything, that the portion of data, instead of it being 34, 13.5, etc., they've got this formula depending on how far out you're going. Okay, now we're going to ignore most of what they're saying here and just focus on these things. Okay, and then let me give you a picture. So if you go out, so here's one group, there's the average right here, right? If we go out 1 standard deviation, Chebyshev doesn't tell us anything. But if we go out 2 standard deviations, Chebyshev now says that if we go out 2 standard deviations, then we're going to cover at least 75% of our data. And if we go out 3 standard deviations, right? This is -1, these are plus. If we go out 3 standard deviations in either direction, we get at least 89%, 88.8. Okay. If you were to go out a fourth one, which this graph doesn't have a fourth one, then it would cover at least 94%. Okay, so that's the thing here. So with empirical rule, it's exact, but it's only true for bell shape. With Chebyshev's, it's at least, but it's true for any shape. Okay, so let's look at this example. The age distribution for Georgia and Iowa is shown in the histograms. Apply Chebyshev's theorem to the data using 2 standard deviations. And what can you conclude? Is an age of 100 unusual for Georgia resident? Okay, well, we're not even talking about Iowa, so who cares about Iowa right now, right? We're only talking about Georgia. So let's look at this just logically for a second. Is the age of 100 unusual? Do we see anybody that went out to 100 over here? No, nobody even went out that far. So it does seem unusual. But it says use his theorem for 2 standard deviations. Okay, so let's see. We got 37.3. So we're going to add 2 standard deviations and we're going to subtract. So plus 2 times whatever standard deviation is, and minus 2 times whatever the standard deviation is. And they told us that the standard deviation was 22.3. Instead of me doing some really bad math, I'm going to skip ahead to the next deal. But let's think for a second. 37 minus 44, that's going to be a negative age. It's going to be a negative number. That's not even going to make sense. So we'll just use the number 0. And if I'm going to estimate without a calculator, because I don't have one in my hand, 37 plus 44 is, Flannery can't math. 37 plus 44. 7, 8, 9, 10, 11. That's 81. So this is a little bit older than 81. And remember, going out to Chebyshev's theorem says if you go out 2 standard deviations, you're going to hit 75% of your data. So 75% of the people in Georgia are between the age of 0 and 81. So yeah, 100 would be unusual. Let's look at what they said officially. Okay, so they did the whole, use my little pointer now instead of my pen. They did the whole 37 minus 2 times the standard deviation, which was a negative number and can't have a negative age, right? And then they added 2 times the standard deviation, which gave them 81.9. So it says you can say that at least 75% of the population of Georgia is between 0 and 81.9 years old. So yeah, 100 is unusual. 100 would definitely be unusual. Okay. We are going to skip through this week. And we may not get to it. It's not hard, but we're just going to, we're focusing on certain things for COVID, not everything. We're going to skip this. But we are going to talk about coefficient of variation. Because if you have 2 sets of data and you want to talk about which one is more spread out than the other one, you have to have some way to compare the 2. And the best way to do that is to compare them to their average or their mean. And that's what a coefficient of variation does. It says it describes the standard deviation as a percent of the mean. So you take your standard deviation, you divide it by your mean. Okay, whether it's the population or whether it's the sample, you take the standard deviation and divide it by the mean. So In this example here, it says we've got heights and inches and weights of people on a basketball team. Find the coefficient of variation and compare the heights and weights. There should be a T right there. That's a typo they made. I'm not the only one. And then compare the results. So we're going to figure out the standard deviation of this height, and we're going to figure out the standard deviation of the weights. But we're going to kind of cheat. We're going to let them tell us. So the average height was 72.8 inches, and the standard deviation was 3.3. So we just take that average height, the 72.8, and the standard deviation, and we divide them. Okay, so 3.3 divided by this, multiply it by 100%, you get 4.5. So that is the coefficient of variation for the height. Now we do that for the weight. The average was 187.8 pounds. The standard deviation was 17.7 pounds. So we take that number, divide it, turn it into a percent. So we get 9.4%. So if we're going to compare those two, the weights was 9.4% variation. And the heights was 4.5% variation. So even though we're talking about pounds and inches, even though those units are totally different, if we pop them into percent and compare them to the average, then we can compare them to each other. And we can say, yeah, the heights are less spread out, the weights are more spread out. Okay?